claims made before and to make some preparation for Kevin's talk. So we have three main goals. I will first write down here. So they may or may not be related to each other. So the first thing has to be with this slope counter. So we always say it's almost their quotient. And the first goal today is to say indeed for any quasi-compact open from U to from G. So we will show that this is their quotient. So this is our goal one. So during this, we will develop a general paradigm to prove something things like that. And we will also see like log spec is also almost a their quotient and things similar to that. Let's go one. Let's go two. Each approach does not look like something related to the before. In fact, they do. So this is the second half of this ambidexterity. So recall Dennis want to show this LG cast. So it means a left joint and right joint, and these joints are equivalent. So in his talk, he showed that the left joint is equivalent to the dual functor, and now I will show the right joint is also equivalent to the dual functor. So here we are abusing notation because the dual functor is actually a function between the dual categories, but we are using the self dualities for these categories, just like what Dennis did. And go to will finish this ambidexterity in particular. So you can talk about the one ring that controls them all. So the AG cast. So defined by Dennis. Recall models by definition. So tensor ring is the monad calculating. I think let me hope I wrote it in the correct direction. So this endomorphism functor, which go from Q what says G check to itself. So Dennis defined such a thing, which is actually algebra inside this symmetry modular category. And goal 3 is to give you some property about this thing. So namely, I will tell you how to calculate it in terms of operas. So the claim is if you
log is irreducible. Right?
What?
Log is irreducible. That you call
of course. Yes. Okay. So so if we look at a point for simplicity, look at the point of this irreducible locus. So I will tell you how to calculate the fiber of this guy. So namely, so the fiber of this guy is given by singular homology of something, and this something will be recorded soon, but let me first leave it at that. So I will just tell you it's some singular homology. In particular, you know, so its homology degree is greater or equal to 0. Sorry, smaller or equal to 0. And Kevin will use that property to deduce something. So these are our goals. And I think I have 85 minutes for that. So shall we start?
Just quickly, is the image of localization, does it land in Caspidal or again?
Which thing?
Of the Casimudi localization.
No. So the image is not cuspidal. So recall the image is contained in temporal part.
Yeah.
But you can further like project onto the cuspidal part. Then you will see that this compilation is their quotient, because cuspidal part is something only on quasi-compact open. This is something stronger than not cusp being quotient. Okay, now let's start. Let's finish go 1, and then maybe we will take a break. Let me first tell you some general paradigm. So which tells you how to one way to prove some function is a vertical quotient. Suppose you have a function from C to D, let's assume C and D are compactly generated. So therefore, the quantum joint of this function is continuous. And that is defined what he called F of, which is a bad notation, I believe. So I will use the notation F count. So count for conjugation. So it's the conjugate function, so which is a function from C due to D due. By definition, so it's the due of this right quadrant, and by some formal thing, you also know it's the natural joint of the due. So because due interprets natural joint from the right quadrant, so it's some function. And if these are given by some geometric thing, so like D modules, so usually if you use some function for Schritt push or star push or something like that, the conjugate function is given by similar push or pull, but you change Schritt to star and star to Schritt. This is usually how you think about it. So now let me give you an exercise, which is actually a construction. So because we assume C is unitable by the definition of few things of few categories, you know that exists an object here that for unit 1 inside this thing that witness this duality. Just think about dualities between five-dimensional vector spaces. So you have some particular element in the tensor product of B and B due. This is like a categorification of that. You have this object. So if you want, knowing an object here is equivalent to knowing back to this tensor product, which by definition is equivalent to knowing C to C, and this object corresponds to the identifier. So similarly, there's this object which is D tensor D due. So you can actually write down these objects as some coordinates, some coends of x box times this the due of x, but I will not write it down. So what I want you to do is to construct a morphism between the following objects. So on the left hand side, you consider F tensor as F touch, the conjugate function. You apply it to.
We just say what Lincoln's contract will call.
Yeah, I said that. But I don't want people to. Okay, I mean,
It's
so we apply this function to unit 1. So note that unit 1 is object in the principle that we apply F here and F touch here. So it becomes an object here. So at the end, there's always a map from this guy to unit 2. Oh, this is an exercise 44. So if you want, you may use this unit 1 as some coend and use some functionality of coend to produce this. Or you can do this exercise for fundamental vector spaces, which is also something very stupid. That's so interesting.
But let me just say, if you translate this all into this happens in D tensor D check, aka endomorphisms of D, and if you translate what the source is, just F composed with this right examples.
Exactly.
And that's just very general things about this whole setup of like it's like the rule of the right like we have F tensor D check, and then it corresponds to the composition of F and D.
Exactly. So Sam just gave you the hint to the next exercise I'm asking you to do, which is the general problem I'm referring to. So claim the following equations or the following conditions are equivalent. So the first is F is a vertical quotient. This is equivalent to say the F count is a vertical quotient, which is also equivalent to that morphism being inverted. So intuitively, so you should think this unit 1 as some object in the tensor product that controls the entire category. And in some sense, this tells you that all information about D so are controlled by information about C.
Can I ask you also just to write that it's the same as FR eventually makes more sense?
Of course, yes. So this is some exercise for you to recall. So what's the action? So it tells us that if you want to prove some function is a Verdell quotient, you can try to provide some duality and calculate the continuous function and apply them to the unit object for this period and to significantly match with the other unit object. And this is exactly what we are going to do. So far, any question? And, okay, so your question is what's the meaning of being a Verdell quotient? Yeah, so it means the following. So F D to D is a Verdell quotient if and not if let's have R is. This is my definition.
Nick says that's what's called a Gaussian filter.
Yeah, of course.
Well, no, Verdell quotient means something else.
Means what?
Well, it doesn't require any expansion. It's not about small.
Oh, yes, of course.
Something deep. Something
Okay.
else.
Let me talk about the quotient.
But that's
It's okay, then let's proceed, that's the definition.
Okay, so the first application is to this localization function composed with this J upper star. So let me write out the for one. So which says that this J upper star node is a quotient function. Well, it's a quotient. So I will sketch the proof for you. So like here we should the very first step is to show this function to the compact objects so that we can talk about its conjugate function. And let's prove this. So recall this KL1 is compact generated and there's a function that gives you the compact object, namely this induction function from representations of this R group to this KL. So this is int. So this function preserves compact objects and essentially all compact object here comes from compact object in L plus G. So now we apply this log to B of bond G and then apply this get upper star to B of U. And I will write down some computer diagram which we have seen before. So here we can do this log Q code, and this is Q code bond G. So in my talk, in Sam's talk on Wednesday, so he explained that this diagram commute because similar thing holds for any localization of the algebra of horizontal pairs. So the next diagram commute, and of course here you can also restrict to Q code U and this diagram also commute. Yes, indeed. So therefore, so we can do some diagram tracing. So we want to show the top horizontal arrow preserve compact objects. So this vertical arrow, so it controls all compact objects. So you only need to show that the other arc preserve compact objects. So but we know that. So namely, so let's look at this computation. So you first do this log Q code and do this J upper star. By definition, this is just star pullback. And now let me draw a diagram. So it's not just star pullback. It's given by the following thing. So you start from something here, which is BL plus G1. You start pullback to U times 1, and then you do integration along this 1 direction to go here. So this star pullback function at the midst of continuous right adjoint because this U is quasi-compact. So its right adjoint is the star direct image. this integration and then run, so also admits a complete right joint for the strict pullback because this run is something, it's the union of some properties. Here, union actually means coordinate. So therefore, both of these functors admits continuous right joint, which tells you that this functor preserves compact object. And we have explained this functor generates the compact subcategory. So therefore, we reach the conclusion that the top horizontal functor also preserves compact object because this thing also preserves compact object. So this means at least we can talk about conjugate functors for this computation. So note that you do need U to be quasi-compact. That's a reason we need here. Any questions so far? Now let's do duality.
The question is, maybe just remarks. Earlier, it was many sandstocks that you fix, you points of the curve, you put them down in weights. Localization is a differential operator, it depends on the thing, and this is some version of that.
Yeah, indeed. So for now, so we are doing something pure formal. So you don't even know what's KL. This game is until we do some real calculation where you need to know something. But now I'm just playing formal games. So now let's do duality. So as explained by Herbert before, so this KL is self-due. So by in some fancy way, so D modules and the quasi-compact quasi-compact stack is also self-dual via this real duality explained by Dennis. So therefore, so we can identify the two categories of this. The source and target of this function is themselves. In particular, we can abuse notation by writing the conjugate functor of this thing as some functor between them. And now I will make a claim, so which is an exercise. I will explain how to do this. So which says that this functor is self-conjugate. Via the above duality. Self-dualities. So I think everyone understands what's the meaning of this statement. Good. So now let me explain how to prove this claim. So you can first try to do this similar thing for localizations of finite cavity algebra. You may want to do representations for this Harry-Chana pair to D modules on this bicuta quotient by K, as in Sam's talk. And unfortunately, if you really do it carefully, so you will see that this functor is not self-due. So because the difference of left D modules versus right D modules. So here, there are actually two versions of D modules, maybe write L or R, and you can do a left localization or right localization. Exactly by putting these things on the left or on the right. Maybe there's a commercial shift, I don't care. So you have approach these two functors. And if you really calculate it very carefully, you will see that the left localization is conjugate to the right localization, something like that. So this is leave an exercise for you. So you may wonder, okay, so this means something like that cannot be true. But remember, we are working with critical level. And this critical level is in fact like 1/2 of left D modules plus right D modules. So I know this does not make sense, but you may remember that the difference between left D modules and right module are controlled by this United complex on your stack. And this critical twisting square is exactly given by this United complex. So, yeah, that's not one. Yeah, because it's smooth. So therefore, I'm saying this difference appears when you look at critical level. That's why we have this result. So it's self-dominant. Self-dominant. So any questions so far? So now we can apply this paradigm. And we only need to show the following thing. So we apply log, tensor log to the unit for this Casinoti pairing. So which is some object that I haven't defined. I will tell you some information about it later. And we do this J upper star, tensor with J upper star. So because that's what we need to do here. So we do F tensor F count. F here is log followed by J upper star. So this is the left hand side. We obtain a morphism from this thing to the right hand side, which is the unit for the Medea pairing. And by definition, it's the you consider the Dunizing shift on U, and you do direct image along the diagonal base. And now I want to use another notation for it. I will write it. Third control star the RAM to indicate we are dealing with D modules. We push forward a D module because later I also need to push forward some O module. So I want to distinguish these notations. So we obtain this morphism. So if you want, this is unit 2, this is unit 1, and we only need to show this morphism is invertible. This is the goal. And I will prove something stronger, which allows you to get rid of this JRP star. It says that if you just look at the thing before restriction, so this guy is actually same as you do this direct image for this omega bound G. So here, now this delta is the diagonal morphism for bound G. Note that we no longer do quasi-compact stacks. So we are doing really the entire bound G. But this morphism is actually relative quasi-compact. So which allows us to define this the direct image. So I connect.
But it's like a D module on Bungie is for every U there's a D module. Because we kind of wins, yeah.
Yeah, then I'm going to say this equivalent and taken limit. Yes. A prior stronger sequence. In fact, that I couldn't. Okay, so I will prove this. So and in fact, so you can use this this calculation to prove the things that I named yesterday. So where I say this vanishing conjecture, so can be obtained by something about KL because log is almost surjection. So using this thing, so it's easier to formulate that. If you are interested, you should ask Joachim about this and learn the argument from him. Okay, so this is something we are going to do. Let me call it key calculation 1. Key calc 1. And the paradigm tells you that this key calculation 1 implies this calculation 1. So this is something we should do. So instead of giving you the complete information about this key calculation 1, let me write down many remarks which explains why this thing should be true. So the first remark, maybe it's not necessary for this calculation, but it's very useful. So I will tell you what's this object. So Gerber failed to explain what's the pairing functor. So because this saving infinite cohomology is something kind of hard to explain, but this unit object has some very at least intuitive description. So this unit KL is something called Caddo. So it's called Carroll algebra differential operators in the book by Griffith Discovery. So now I'm going to explain this. That's further development of the in the paper by article what? Yeah, benefit and trivial and further developed in article and textbook. Yes. It's the following guy. So we consider this D module on LG. So this LG is acted by itself both from the left and from the right. Therefore, by our general paradigm of localization, this gamma functor, here gamma means gamma for Q call, or maybe better, gamma for int call. So because this is some indexing. So you do gamma for int call, it will factor through some representations for the Lie algebra of LG times LG, coming from the left action and the right action. So it will go to this guy tensor with itself. So this action coming from the left, this action coming from the right. And recall this guy is a factorization category. So there's a factoring unit here. So which is given by the third party module supported at the arc group. This is actually the factoring unit. We just send we just consider the image of this thing, in other words, consider it in the total global section. So that is the catalog. So here I have to justify that the result is integrable for the arc group for on the left and on the right. That's because this object is L plus G plus L plus G int because this orbit is. So therefore this thing is L plus G plus L plus G integral. So that explains why this object is contained in KL tensor KL, because that's the definition. And the first remark tells you that this cuddle is actually given by this object. So this is our unit one. That's just some additional information which might make you feel easier. If you don't believe this, so you can try to do the same game for just finite type group G. So you will produce some object in G mod, tensor G mod, and I claim it's still the unit for the Perry. Maybe up to some shape. Any questions so far? Yes, it's the unit for the self duality of KL. Yeah. If you want, I just open the black box for the self duality of KL. Okay, so now maybe this. I will run this. Mark 2. So previously, we are talking about the we are talking about this horizontal function. And you can ask the similar thing for the bottom horizontal function. It turns out the same story still works. So I will just say this function is still okay. In the following sense, so you have this key calculation tool, which tells you if you just do log Q call and some log Q call to the unit of this rep G check, to the unit of this rep L plus G, which you may know is the regular representation. So you will exactly get the unit for the period for Q call, which is the direct image of O on this function. So this is key calculation tool. And just like before, so this key calculation tool implies, or actually equivalent to the statement that this log Q code J star is a quotient for any J.
I think Brugier has a question. You could maybe.
Wait, you have a question?
Yes. Are you going to prove calculations 1 and 2, or are you assuming them?
I will explain how to do this.
Okay.
Okay, now I'm going to explain how to deduce calculation 1 from calculation 2. That's remark 3. I will leave it as an exercise, but I will give you some hint. I will say T2 implies T1. So the hint is given by the following formula, which is quite elementary. So you apply this in tensor ID to the unit of this well plus G, then it's equal to you apply ID tensor octave. So apply to this unit KL. Now they will cut. So let's look at the type of let's look at the type of these objects. So this is something in red, infrared. You apply in on the first factor to become an object in KL infrared. Similarly, this is something KL is a KL. You forget the second one, you go to KL infrared. So you give that in the same category. And like them, they are the same. And this actually follows from something much more general. So in general, in this story, I claim F tensor ID applied to unit 1 is the same thing as ID tensor F2 applied to unit 2. So that's something Sam told you before in words, but that's the place where I want to put it now. Yeah. So we just apply this exercise to self-duality for this thing, we will get this form. And I claim using this formula, it's easy to deduce K calculation 1 from K calculation 2.
And let me just make one technical comment that you're gonna make in the future also. Giving that to you, but just like morally, P calculation 1 and P calculation 2 are the same order of difficulty. And so you might think if you can do P calculation 2, you could just put down the same argument to do P calculation 1 directly. But it's actually convenient to distinguish between the two of them because there are some technical little like things Lynn's covering up here, like there should really be some semi-infinite cohomology popping up, and like that was comparing we learned before. And so the state extension, blah blah blah. And so there's a little bit of whys in part 1, but there's no whys at all in part 2. And so like, what you're trying to do is kind of erase that technical thing to make it just a calculation you can do it.
Okay. Yeah, thanks for fun. And now instead of give you the calculation tool, so I will give you another key calculation, which is of the similar favor. I think work. And then I will explain how to do that. So that's is my remark 4. It is. So same story if another node on the board, namely the spectral node. So which go from this rep G check to Q code log says G check. Yes. So these categories that still self-do, and even better, now this guy is actually fuzzy compact. We do not need to worry about this non-continuous functions. So now I will tell you what's key calculation 3. So it's you apply this like before, you can show this log spec is self-conjugate for the self-dualities. You apply it to this unit, which is again regular representation used as a fraction order. So you apply this. So the claim is you get the unit for the self-duality on log says G check, which now is delta nova star for all on log says G check. So this is key calculation 3, and just like before, this is almost, I think it's actually equivalent to the thing we claimed before, which tells you that this log spec is a quotient function. So in other words, So I have just wrapped up all the unfinished plans about this faithfulness or quotient we made before. Yeah. By reducing them to some key calculations. So any questions so far?
Yes, the proposition you first showed that J upper star logs preserves complex.
Yes.
How did you use this in the further proceedings of proof?
Oh, so we need this complex list because this paradigm. Well, I already erased that, but this paradigm, so it's something about f and the conjugate function. Even to define this conjugate function, we will need this function to preserve compactness. So, but yes, but when you arrive at that, so you arrive at some formula, and you can just take limit for that formula and to get something which does not contain this J. So this is what we did. So
Yeah, in other words, there was a lemma that was referred somewhere, which said that you take the right adjoint to localization, and then you take the dual that's the same as localization, and even the statement of that lemma, which was like what reduces to this calculation, it only parses for classical opens because of this preservation of non-calculations. Yes, yeah.
So people agrees that these functions are isomorphism.
yes, of course. Okay, so now let me give you some ideas how to prove this key calculation 2 and 3. So they are just some calculation which is a relative version of Lick's calculation in his talk. So just relative. So namely, to recall, so we use this formula for many times. If you have a D scheme, F and D scheme over X, you can consider the global horizontal sections of this D scheme and consider the function on it. So it's given by some factorization homology. So in other words, some push from the run space of some factorization algebra, and this factorization algebra is the function controlling this this alpha D scheme. In other words, its functions on this horizontal arcs. So we have used this for many times. This is the absolute version. So corresponding to the case D maps to put. So there's a relative version of this which I'm not going to write down. So but it has to do with maps from some Z to some Y, which is alpha. And in this case, what we are going to do is we are going to apply this to BG check, maps to BG check times BG check. So this is alpha morphism, and here the right hand side is some local thing, so it will become this, and the left hand side is some function on global guy, it will become this. So note that this thing is exactly the alpha algebra on this G check comes to this G check that controls the diagonal. So just like what's happening here. So are people happy with this argument?
Is there logical implication between key 2 and key 3?
No.
Sorry, key 3 and key 4, sorry, key 3.
Where's the key for?
No, key 2 and key 3, sorry.
There are no logical thing between them. So one is on G, other is on G check.
No, but
Yeah. So okay, so this is for key 3. And for key 2, you just use the main restriction of the thing, but for BG. So here, this main restriction means along the map from X to X to 1. So which is something
Lena, I think Eva was asking if you can forward me to something like that. I don't think you can, but you should apply it to a different guy.
yeah, I think so.
I think you got it, yeah.
Maybe, that's not.
Yeah.
Yeah, maybe. Okay, that's remark 5. And remark 6 is something, oh, by the way, so at this stage, so I think I have explained how to do these P calculations. And by previous discussion, we finished the proof of goal 1. Yes. So are people happy with this? Let me give you some additional remark. So look at this fundamental diagram. So we have used the same trick to do this functor and this functor and try to prove that this is almost a quotient and this is almost a quotient. You may wonder, can you do the similar thing for other functors? This Poincare automatic set and Poincare unspectral set. The answer is this is too difficult. I don't know how to do that. So for instance, on the autonomic side, you may want to calculate this Poincare shrink. Turns out this Poincare star. Note that these two factors were introduced in Danny's lecture in the morning, so they are conjugate to each other. So you apply this to the unit of V hyper. So you may want to say this is the same thing as the Taylor star of omega upon G, but we don't know this a priori. So can't prove this.
It's not true, right?
It's true.
No, it's only temporary.
It's true.
Oh,
Delta lower star.
yeah, that is what it is.
It's like similar story like before. Yeah. Okay, so that's for go 1, and maybe we can take a break.
Yeah, how many, like, 10 minutes?
Really, so.
10 minutes break. Terrible stuff will come after.
Yeah.